I'm glad to be here with you today to talk on biochemical evidence that God created life. My name is Jim Perkle. I'm a board-certified clinical pathologist, and I also have a doctorate in physical chemistry. My current job is that I'm the director of 25 research and reference laboratories that specialize in measurements of peptides, proteins, lipids, carbohydrates, glycolipids, glycoproteins, DNA, RNA, organic compounds, and elements. These 25 laboratories rely heavily on advanced mass spectrometry techniques and also newer molecular diagnostic techniques. If you're interested, further information about me can be found at jimperkle.org. In 50 plus years of scientific investigation, my experience has been that the deeper we look into science, the more we find evidence for God's handiwork is thoroughly compelling. And that's one of the reasons I wanted to talk today about the topic at hand. The presentation I'm making today draws from material in my book, Choosing Jesus in Science. And this book is available on Amazon, both in paperback form and Kindle. And also a free PDF is available at jimperkle.org, a free PDF. So the essential question I want to address today is, can undirected assembly create life, or is directed assembly required? And that'll be the main focus of the talk. In brief, this outline covers 5 areas that I want to go through. The first is providing background and context for can undirected assembly create life, and then to go over that random processes make genes and natural selection and genetic drift preserve genes. Next, look at interpreting low probability levels, and then a review of the binomial probability formula. And finally, we'll do some calculations that calculate the probability of undirected assembly of a 400 amino acid protein, the heavy chain of dynein, titin, and other proteins in the cell. It's best to start off by defining some terms. Evolution, as it's commonly used, refers to really 3 different things. The first is that undirected assembly created life. That is, that life spontaneously arose from non-life. And that's going to be the topic of most of today's discussion. The second is within kind adaptation, or microevolution. And this is the concept that there can be small changes, but the particular organism stays within species or within kind. And this is like what we see with COVID now, with the COVID variants. It changes a bit, but it still stays a COVID virus. And then between kind macroevolution. And between kind macroevolution says we started with one organism that was kind of the great-great-great-great-grandparent of all of us, and all the diversity of life emanated from one organism. Now, what parts of evolution are contested? This is one of the good reasons to break it up into 3 parts. Because the first part, that undirected assembly created life, does not agree with the Bible. The Bible says that God created life, and that undirected assembly cannot account for all of life. The second part, that within kind adaptation, is perfectly compatible with the Bible, perfectly consistent. There is no conflict between microevolution and the scriptures. Now the third part, between kind macroevolution, that says we all descended from a single organism from random changes, does not agree with the scripture. And the scripture definitely talks about God creating different kinds. Now I'm going to talk just for a few slides on between kind macroevolution, but that's not the major part of this talk. But there's much more material on this in my book, but I want to highlight a few points that I think are very much merited. Between kind macroevolution can only use gradual, piecemeal, random changes to create. The creation force of between kind macroevolution is random changes. Natural selection and genetic drift cannot create. They can only preserve. Natural selection can only preserve a gene after the gene has been made. Natural selection cannot make the gene, and the same is true for genetic drift. So all the creative ability of macroevolution lies in random change. So when we look at the possibility that a first organism went through just random changes and made all the biological complexity of the hornet, and we look at the possibility that a first organism went through all those random changes and created all the biological complexity of a kangaroo, to me this is overtly untenable, that creation from random processes could bring such order and beauty and complexity and interdependency together. Now that's looking at kind of a large-scale biological view, but once we take a look at cell biochemistry, we find that the staggering complexity of cell biochemistry stymies macroevolution. Cell biochemistry is not just complex, it is staggeringly complex, with layer upon layer upon layer of highly interdependent molecular systems that are precisely interacting for cell function. I generally tell people that if they will take a look at the complexity, that they will for sure see the handiwork of God in cell biochemistry. I'm just going to give one example here. Protein and chemical systems that require multiple components to function are an overwhelming barrier to the gradual piecemeal steps of macroevolution. So for example, if we had a protein complex, and there are many protein complexes in the body, if we chose one particular protein complex of 10 proteins, that complex needs all 10 proteins to function, and that's shown here on the graph, with function on the y-axis and number of proteins available on the x. If you just had one protein, that complex wouldn't function. Even if you had 5, even if you had 9, that complex would not function. And yet macroevolution has got to proceed in a sequential, gradual fashion, making one protein and then having natural selection keep that protein around until it can make the next protein, and then have natural selection keep that protein around until it can make the next protein. And what we would see would happen is if it made a protein in this complex, it would serve no useful purpose, so natural selection would not keep it around. So anytime we have protein and chemical systems that require multiple components to function, this is a huge barrier for macroevolution. It just cannot account for how these protein complexes exist. And to give one more example dealing with cholesterol, this is a little bit busy slide, but the synthesis of cholesterol is shown on the left. So it begins with farnesyl pyrophosphate and goes all the way down to end up with cholesterol. Now there are 9 synthetic steps here to make cholesterol, and it involves 9 different enzymes. The 9 different enzymes to make cholesterol have no other use in the body. This is the only place they are. They have no other use in the body, and the intermediates in the cholesterol pathway have no function other than to make cholesterol. So none of the 9 enzymes by itself improves survival. So none of the 9 enzymes would be preserved by natural selection. But all are required for mammalian life, and you and I would be dead if we could not have cholesterol inside of us. So this again is another multi-component system that natural selection and mutation with natural selection just simply cannot account for. Now early on, we had prokaryotes that do not have nuclei, and prokaryotes do not have cholesterol. So somewhere in the process, moving from prokaryotes to eukaryotes, cholesterol had to be made. And since cholesterol had to be made and natural selection and mutation cannot account for how it's made, we find here a fact that is incompatible with mutation and natural selection, the cornerstones of macroevolution. Now these are just 2 examples. There are many other examples, including oxidative phosphorylation, the way we get energy in our body, ribosomal protein synthesis, the way that we actually make proteins in our body, DNA transcription, how we reproduce cells, gene regulatory networks, all are excellent examples, and there are many more. And these are detailed in my book, and like I said, I'm only popping off to deal with a couple of these as examples going by the way here. Today's talk, like I said, though, is going to mainly focus on can undirected assembly create life? So I'm going to formulate the question to say, can undirected assembly make the proteins in the mammalian cell, or is directed assembly required? And the one key point I want to make here is that if assembly of proteins is not undirected, then it's directed. There are only two choices. It's either undirected or it's directed. So we're going to take a look at the probability that undirected assembly could make the proteins in the mammalian cell. Now, what's the reason to focus on proteins in mammalian cells? And there are a couple of good reasons. The first is that modern mass spectrometry measurements have provided excellent data on structure and number of mammalian proteins. So we have done lots of analyses in mammalian cells, and we know the average protein size in a mammalian protein is greater than 400 amino acids long. We know the number of proteins in a cell is greater than 16,000, and we've done a lot of characterization of these proteins. And the second reason is that mammalian proteins did not exist in the prebiotic environment, so they had to be made at some time. And so these two reasons really help us to focus on mammalian cells. As you'll see, we're not focusing on anything like a protocell. Protocell is not needed, and we very much understand the characteristics and the properties of mammalian cells, which gives us a more precise and a more accurate scientific question to answer. So the second thing I want to move to now is random processes that make genes, and natural selection and genetic drift that preserves genes. So random processes that make genes, and again, genes are what code for proteins. These include the original DNA synthesis, mutation, which has got insertion, deletion, and substitution, recombination, gene duplication, translocation with transposons, gene fusion. All these things are random processes that go on, and these help to make and modify genes. Now, natural selection and genetic drift, as we mentioned before, can preserve a gene once it is made. But natural selection cannot make a gene or alter a gene. It can only preserve a gene, and the same is true for genetic drift. Now, natural selection and genetic drift do not affect the calculated probabilities that we're going to do for undirected assembly because natural selection, as we said, cannot preserve the gene until the gene is made for the first time. And the calculations that we are doing is the probability of making the gene that codes for a protein the first time that it is made. So natural selection doesn't interact. We're trying to figure out the first time this gene is made, what is the probability that it can be made. So natural selection and genetic drift will have no effect on the calculations that we're doing here for undirected assembly. The probabilities we're going to calculate are also not affected by the presence or absence of protocells. It doesn't matter if such and such protocell was the beginning of life or not. It doesn't matter if there were 7 or 8 or 10 sequential protocells. It will have no consequence on the calculation. Nor does the presence or absence of intermediate proteins. Doesn't matter if a protein hung around for a long time. Doesn't matter if a protein quickly went away. None of that will be consequential in these calculations. And things like master regulator genes like Hox genes will be totally irrelevant to these calculations. And it also will not matter when in the course of time that the assembly took place. So these things are things we don't have to be concerned about because of the way we're doing the calculations. So the third section of our outline is interpreting low probability levels. So we're familiar with some probabilities readily because of our experiences in life. We know what a 1 in 10 chance is. That's a probability of 10% or 10 to the minus 1. We're familiar with 1 in 100 is 1% or 10 to the minus 2. And we have some experiences with 1 in 1,000 or 0.1% or 10 to the minus 3. But what about lower probabilities? And we're going to be talking about low probabilities here. So it's useful to get some sort of connection to what low probabilities mean. So I have two examples. The first example is selecting one Scrabble tile from a room full of Scrabble tiles. So imagine you had a room that was 12 by 16 by 8 feet, and you filled it with Scrabble tiles, floor to ceiling, multiple stacks of Scrabble tiles. And you hid one letter Z tile in all that room, and so here's a letter Z tile. It's a little bit bigger than a dime. Blindfolded, what is the probability that you could select that single Z tile in one try? Well, this can be readily calculated, and the probability is right at about 10 to the minus 8. Well, most of us would consider that something that is not going to happen. You're not going to be able to reach in that room and grab the singular Z tile. But what if we expanded this and we were trying to select one Scrabble tile from Scrabble tiles that filled the volume of all the Earth's oceans? Just think about the time you've been to the ocean and how vast it is, how deep it is. Well, the volume of all the Earth's ocean is about 1.335 billion cubic kilometers. And if we filled all that volume with Scrabble tiles and used only one Z tile, what is the probability in one try of picking that single Z tile? Well, this can also be readily calculated, and it's about 10 to the minus 24. Now, I'm going to refer to 10 to the minus 24 as a zero-level probability, because it is the probability of grabbing one Z tile out of all the tiles that fill all the volume in the ocean. And I'm going to define that as a zero-level probability, something we can anchor to as something that does not happen. And next I want to review the binomial probability formula. And this is going to be very important for our last step when we're calculating the probability of undirected assembly. Now, the binomial probability formula is a mathematical formula, just like a squared plus b squared equals c squared for a right triangle. And the formula calculates the probability p for k successes from n independent tries for an event with a yes or no outcome when the probability of success for one try is known. So this sounds a bunch to absorb real quickly, but we're going to go over a couple of examples. I think this will become clear. So you can see the formula here. In light green is the big probability p. There's k successes, how many times it's successful. You get n independent tries, and the probability of success for one try is little p. And here's the formula shown here at the bottom of the slide. And so here's an example using the binomial probability formula. Let's say you rolled a fair dice 10 times in a row. What's the probability that 4 would result 2 times? Well, in this example, n equals 10 tries because you rolled it 10 times. You're asking for the probability for 2 successes, so k equals 2. And the probability of success in one try is 1 over 6 because 4 is on one of 6 faces of the dice. So if you plug these into the formula and you calculate it out, you see at the bottom that the probability is 29.1%. So this is a very useful formula. It can be used for many things. Now, a particular interesting use that we want to make of it is to look at zero successes. So what does the binomial probability formula reduce to if you put in k equals 0, that there's 0 successes? It never happens. Well, if we substitute k equals 0 into the formula, we can see that it simplifies a lot. Well, it turns out that 0 factorial is 1, p to the 0 power is 1, and as we go down the lines here, we can see that the probability reduces to 1 minus p quantity to the n power. So this is the probability of 0 successes. The probability for one success is that small p within the parentheses, and the number of tries is n. So it's only a function of p and n. So if we wanted to calculate the binomial probability formula for one or more successes, then all we have to do is subtract the probability for 0 successes from 1. So the probability for one or more successes is 1 minus the probability for 0 successes. And therefore we come up with the final formula which we're going to use, which is the probability for one or more successes is 1 minus p quantity raised to the n. And this is the formula you'll see in a blue box and several other slides that we use, but it is derived for the situation where we want to find out what is the probability there will be one or more successes. So just to give you an example using this formula for one or more successes, if we go back to our fair dice and we roll it 10 times in a row and we want to know the probability that 4 would result one or more times. Well, using our formula, we can substitute 0.167 in for the probability of success for one try and 10 tries, and the answer comes out to be 83.9%. So this is an example of the use of the formula. So the important thing to conclude from this section on the formula is that we now know the probability of success, if we know the probability of success from one try, and we know the number of tries, we can calculate the probability of one or more successes. So we really have got to go out and find that little p, and also which is the success from one try, and we've got to find that n, which is the number of tries. And those are the things that we need to go after to evaluate the probability of undirected assembly. So finally, we're going to get to the section where we deal with the calculations of probability of undirected assembly for a 400 amino acid protein, the heavy chain of dynein, titin, and other proteins. Just by way of a little review, a chain of amino acids comes from the ribosome, and that's what forms the protein. So from DNA, messenger RNA comes and heads to the ribosome, and transfer RNAs are also coming to the ribosome. And each transfer RNA is bringing a particular amino acid. And the ribosome is able to link these amino acids together and form an amino acid chain, and that eventually folds on itself and becomes the protein. So this is how proteins are made in a simplified schematic form. Now we want to determine the upper bound probability that undirected assembly can make a 400 amino acid protein. And by upper bound probability, I mean the maximum probability, the highest likelihood. Now, mass spectrometry measurements show us that the average mammalian protein is greater than 400 amino acids, but we're going to target a 400 amino acid protein to be conservative. And as we mentioned before, we need to determine two things. Little p, which is the probability of success of undirected assembly in one try to make the protein, and n, the number of tries available. And then we can use our binomial probability formula for one or more successes to get the probability that undirected assembly can be successful. And that's the number that we're after. So let's look at then the probability of success of undirected assembly to make a 400 amino acid protein in one try. So each codon, or sequence of 3 nucleotides in DNA, can code for one of 20 amino acids, or it can also code for a stop codon. Therefore, the probability of coding for the correct amino acid, the amino acid that we need in our sequence, is 1 out of 21, or 0.04762. And this probability would apply to each of the 400 amino acid positions, so that if you would have a 1 divided by 21 chance of getting the first amino acid right, and after that happened, there would be another 1 over 21 chance of getting the second one right, and after that, another 1 over 21 chance of getting the third one right, on and on and on, until we got to 400 amino acids. Now, I just want to take a slight sidestep to make sure we understand joint probability and how joint probability occurs from multiplying the probability of independent events. So if we calculate the probability of rolling a 4 and then a 3 in 2 rolls of a dice, the probability of rolling a 4 on the first roll is 1 over 6. The probability of rolling a 3 on the second roll is also 1 over 6. So the probability of rolling a 4 and then a 3 is 1 over 6 times 1 over 6, which is 1 over 36. So we multiply the independent probabilities to get the joint probability. And so it's summarized by this formula on the bottom for 2 independent events, that the probability of A1 and A2 occurring is the probability of A1 occurring times the probability of A2 occurring. And we'll use this formula several times. So if we're calculating the probability that undirected assembly can make a 400 amino acid protein in one try, we use this formula we just derived, which is the probability of amino acid 1 being put correctly, probability of amino acid 2, amino acid 3, and we multiply all those together as shown here, and that equals 0.04762 to the 400th power, which comes out to be 1.3 times 10 to the minus 529. So now we have our one try probability, p, which is half of the distance that we need to go. Now, one try will clearly not work because its probability of success is 10 to the minus 529. But many tries are available, and this is where the contentious point comes. There isn't contention that it's very difficult to do in one try. The contention is over how many tries are available. Essentially, the contention is our best estimate of n. What is the number of tries available? So one side contends, well, the time scale's long, there are many genetic events, there's lots and lots and lots of organisms, and they will provide the needed number of tries to make the protein. Now, the other side looks at the same data and says, yes, the time scale is long. Yes, there are many genetic events in many, many organisms, and they are inadequate to provide the needed number of tries to make the protein. So the hinge of the argument comes on what is really our best estimate of the number of tries, and is the number of tries sufficient to be able to make the protein? Now, the approach is to estimate an upper bound for n. The true probability will be less than the probability of the upper bound for n. And so what do I mean by that? So it's essentially saying if you can't do something in 5 tries, you can't do something in 2 tries. And so if we go for an upper bound of the number of tries and that doesn't work, well then fewer tries certainly will not work. So how are we going to estimate this upper bound for the number of tries n? Well, this is the formula we're going to use. First, we're going to look at the maximum amount of time for this to go on. Then we're going to multiply that by the maximum number of genetic event sites. This is where mutations occur, of course, at DNA basis. So the maximum number of genetic event sites. And then we're going to multiply that by the maximum number of events per site per second. And so the units on this will come out in number of events or number of tries. So again, we're going to figure out the maximum amount of time, the maximum number of sites that a genetic event can occur at, and the maximum number of events per site per second. So the maximum amount of time, well, we're going to use all of time. So NASA estimates that the age of the universe is 13.8 billion years. We'll round this up to 14 billion years, which is 4.4 times 10 to the 17 seconds. We'll round this up to 10 to the 18 seconds. So our upper bound estimate of all of time is 10 to the 18 seconds. So this is pretty straightforward. Now our estimate for the maximum number of genetic event sites. Well, it's very difficult to say exactly how many organisms, exactly how many DNA base pairs are sitting in every organism, but we can easily come up with an upper bound. The number of DNA bases in all organisms is negligible compared to the number of atoms in the earth. So to have an absolute upper bound, we're going to use all the atoms in the earth as our number of genetic event sites, and that's about 10 to the 50 atoms. Now we're going to make this upper bound more extreme by using all the atoms in 1 billion Earths, not just one Earth, but 1 billion Earths, and that'll take us to 10 to the 59 atoms. So this extreme upper bound gives us 10 to the 59th power event sites. And again, there is no possible way there's that many DNA bases in all organisms. So this is a very, very high estimate that's ridiculously high, and it's being selected solely to give us an absolute upper bound. I don't want anybody walking away thinking that this is something that I actually consider to be a decent estimate. Absolutely not, but it's to be a ridiculously high number to provide us an extreme upper bound. And then the third thing that we're after is the maximum frequency of genetic events at each genetic event site. So to have an absolute upper bound, we're going to use 1 trillion or 10 to the 12th genetic events per second for each site. Again, 1 trillion events per second. So this would mean that at the genetic site in 1 second, 1 trillion genetic events occur at that site. Well, this is an impossibly high number. This cannot occur. And we're not implying in any way that this happens, but again, we're trying to find a purposefully unreasonable extreme to ensure that we calculate an absolute upper bound for number of tries. So for each one of these 3 things, we've gone to the top, a ridiculously high number, so we can be confident we have an absolute upper extreme for our calculation. So bringing back our formula, the upper bound for the number of tries is the maximum amount of time times the maximum number of genetic event sites times the maximum number of events per site per second. And when we plug in our numbers, we have then 10 to the 18th seconds for the maximum amount of time, 10 to the 59 sites for the maximum number of genetic event sites, and 10 to the 12th events per site per second. And that calculates out to 10 to the 89 tries. Now, the total number of all genetic events and all organisms in all of time is negligible compared to this upper bound of 10 to the 89th tries. There is no possible way there are more than 10 to the 89th tries to be had in all of time, in all the genetic event sites, and in all the genetic event sites in all organisms. So it's important to catch that we have gone to this unreasonable extreme to give the best chance for the number of tries to make this one 400 amino acid protein. So now we have the two variables from the binomial probability formula for one or more successes. Again, this is the formula we derived, 1 minus quantity p to the end. And little p, the probability for success using one try, is 1.3 times 10 to the minus 529. And our upper bound estimate of n is 10 to the 89. So we just need to substitute these into the formula. So when we substitute these values into the formula, we get that the probability for one or more successes is equal to 1 minus 1.3 times 10 to the minus 529, and then raised to the 10 to the 89th power. Now, if you do this calculation, you do it on a simple hand calculator because it doesn't have enough decimal places. Your calculator needs to have 550 decimal places because we're dealing with very small numbers here. And a calculator like that can be found on mathisfun.com if you would like to try it. But you can't do it on a regular calculator. So the result of this calculation is that the probability for one or more successes is 1.3 times 10 to the minus 440, or 10 to the minus 440. Now that means the upper bound, the highest probability that undirected assembly can make a targeted 400 amino acid protein is 10 to the minus 440 power. It cannot happen. Undirected assembly cannot make a targeted 400 amino acid protein, and this is the probability of it happening. So we don't have to be vague. We don't have to say it seems that one expert disagrees with another expert. We have a probability that's calculated that says what is the likelihood that this would happen, and this probability is 10 to the minus 440. Now let's take a look beyond just a regular average 400 amino acid protein, and let's take a look at the probability that undirected assembly can make a large protein, like the heavy chain of dynein. Now the heavy chain of dynein is required for mammalian life. If I took it out of my body, I would die very shortly. Dynein is an essential molecular motor in the body, a fascinating protein complex. And it's made by the gene DYNC1H1, and it is not 400 amino acids long, but it is 4,646 amino acids long. Now if we go through the same calculation that we just finished, and we calculate the probability that undirected assembly can make it, the probability turns out to be 10 to the minus 6,143. Undirected assembly cannot make the heavy chain of dynein, and you and I cannot live without it. If we step up from dynein to titin, turns out that titin is a muscle protein that's also required for mammalian life. If I took titin out of your body or my body, we would die. It's made by the gene TTN, and it is about 34,350 amino acids long. The probability that undirected assembly can make it is 10 to the minus 45,329. We have to have titin to live, but undirected assembly cannot make titin. But undirected assembly still has a more daunting task to face, and that is it must make the more than 16,000 proteins in the mammalian cell. So to be conservative, we're going to target 15,000 proteins with an average size of 400 amino acids. Now, since we're targeting 15,000 proteins, we need to go back and adjust the probability of success for a single try, that little p, and we need to up it by a factor of 15,000, because instead of having one place that can be success, we have 15,000 places that can be success. And so we need to multiply the probability of success for a single try by 15,000. So that changes our probability of success for a single try up to 1.9425 times 10 to the minus 525 power. Now, using our joint probability formula, we can look then at the joint probability of making 15,000 proteins. So you can see that this is a probability for protein 1 times protein 2 times protein 3, all the way up to 15,000. That then translates out to 1.9425 times 10 to the minus 525 raised to the 15,000 power, which comes up to be 10 to the minus 7,870,675. So the probability in one try to make 15,000 proteins is 10 to the minus 7.8 million. Now, we don't have just one try, but we have 10 to the 89th tries as we went through. But since this number is so low, actually adjusting from one try up to 10 to the 89th tries changes the probability very little. Just the last three digits go from 675 to 586. But we're still at a probability of 10 to the minus 7.8 million. So the upper bound probability that undirected assembly can make 15,000 proteins that we know are in mammalian cells is this remotely small number of 10 to the minus 7.8 million. Undirected assembly simply cannot make the proteins in the mammalian cell. Now, just to give you an idea about how ridiculously small that number is, it is in one try finding one atom randomly hidden in all the atoms of the universe, and then repeating that feat 98,000 times in a row. So if you can imagine one atom hidden 625,000 light years from Earth, deep within a star that's fading away, and you have to find that in one selection among all the atoms of the universe, and then you've got to repeat that feat 98,000 times in a row. Again, it just did not happen. Now, a very interesting thing is to expand the number of atoms from 1 billion Earths, which was 10 to the 59, if you'll remember, to all the atoms in the universe, which we know is 10 to the 80th. Now, this actually yields a minimally changed probability. It just changes a few digits at the end. And we still have a probability of making these proteins of 10 to the minus 7.8 million. And one of the reasons that this is important is it puts to rest the idea that proteins could have been made somewhere on some other planet and then brought to Earth, so they didn't have to be made at Earth. This calculation shows you don't have enough tries in all of the universe, in all of time, using all the atoms in the universe as your genetic event sites. You simply are not remotely close to being able to produce these proteins. The probability is 10 to the minus 7.8 million. Now, one consideration is the effect of possible amino acid substitution. Some people have a theory that some amino acids can be replaced by others and still maintain the same quantitative protein functions. And so this is important to look at. It turns out that this theory is extremely hard to defend, this amino acid substitution theory, because we must show that each protein function does not quantitatively change. So if I have one particular amino acid in a chain and you want to say another one could be there and none of the function would change quantitatively, it's a very high bar to show that. You have got to show that the primary functions of the protein don't change. Like if the protein is an enzyme, you have to show that its enzymatic action does not change quantitatively, not qualitatively, but quantitatively. You have got to show its structural functions don't change. And we know some functions of proteins. We don't say that we know all of them, but the quantitative assessment is something we just have not done. We're not able to go in and really get that information for all these proteins. So this is a place that we're really wanting on information. But much harder is that you have to show that all the protein-protein interactions, which we call the protein interactome, don't change. And this is a place that we're just at the infant stage of knowledge. We just are beginning to understand protein-protein interactions. And so to be able to say the protein-protein interactions don't quantitatively change when we make amino acid substitutions is flat something we cannot assess right now. We just don't have the knowledge. But beyond that, you have got to show that the glycan-protein interactions don't change. Now, glycans are the sugar trees that attach to proteins, and most proteins are glycoproteins or have these glycans on them. And certain amino acids will allow glycan attachment and certain will not, and these glycan trees have got various forms. We are at an infant stage of understanding glycan-protein interactions. We simply don't have the knowledge to say what are the quantitative glycan-protein interactions. So this amino acid substitution theory is an idea, but not substantiated by anything like adequate fact. But to completely put it to rest, we've done some calculations on possible amino acid substitution to show that it actually has little effect on the probability of undirected assembly. And the way that we did this is that we chose an unreasonably extreme substitution of 20% of each protein's amino acids with any other amino acid. So if you had a protein that was this long, then we would say you can take 20% of that protein and take those amino acids and switch them out with any other amino acid, with 19 other amino acids. Any other one can go in those positions. You can totally manipulate completely 20% of the protein. Well, this is an unreasonable extreme, but it is actually just to test what effect it would have on our calculations. And the probability changes from 10 to the minus 7.8 million to 10 to the minus 6.2 million, which is a very small change and doesn't change our conclusion in any way. So the possibility of amino acid substitution does not account for these extremely low probabilities, and we're able to deal with really a very good estimate of the likelihood undirected assembly can make the proteins that are in the mammalian cell. Now, I've done a calculation here for 15,000. There are calculations for varying number of proteins, 10, 50, 100, 500, 1,000, 5,000, and 10,000 are in Appendix B of my book. So if you want to see the numbers for those, there are also vanishingly small numbers, but those are provided in tables in Appendix B. So where does that leave us? So that leaves us with a conclusion that we can be very confident about, that the probability that undirected assembly can create mammalian life is much less than 10 to the minus 7.8 million. And this is something that we can have high confidence in, that it puts to rest the whole idea that undirected assembly can account for life. Now, if undirected assembly did not happen, then directed assembly did happen. If directed assembly happened, that requires a director. So a director is required for mammalian life. And we've shown that clearly, and it's something that we can have high confidence in. A director is also required for the extreme fine-tuning of the universe for advanced life. And this is very much worth looking into. We'll cover this in the book. Very important to see that random events cannot account for the fine-tuning of the universe for advanced life. We also know that time, matter, and space had a beginning, requiring a creator who transcends time, matter, and space. So God is, and the most important thing is God cares. Thank you very much.